Remember Alice and Bob are twins? Alice likes to stay at home, and Bob is always rocketing off somewhere. Let there be a new person, Carla, who is floating through space at some arbitrary speed v relative to Alice. Alice can use the differential form of the time dilation formula to keep track of Carla's proper time. As we have seen in a previous video, this formula can be manipulated to suggest a formula similar to the Pythagorean theorem by making the substitution that v equals dx by dt. The right-hand side of this equation is a function of Carla's changing coordinates according to Alice, and the left-hand side of this equation is the negative of Carla's squared proper time change. This equation that relates an object's changing coordinates to its changing proper time is called the metric equation. Alice and all other inertial observers in flat space-time can use this metric equation to calculate Carla's proper time change, even though they may be moving at some constant speed relative to one another and therefore disagree on Carla's velocity. Bob, on the other hand, is not moving at constant speed and uses his Rindler coordinates to describe space-time. Therefore, his metric equation will have a different form from Alice's, because he is moving at constant rest frame acceleration a0. Let's find out what his metric equation is. First, let's take the derivative of this equation. Now, let's take the derivative of this equation. Now let's square both of these equations. Now let's subtract. Now let's multiply the a0 squared through the last two terms. Now let's factor out the x prime a0 plus 1 squared dt prime squared from the last two terms. And we factor out the dx prime squared from the first two terms. And now we use the hyperbolic trig identity that cosh squared minus sinh squared equals 1, and we make that substitution. And now let's put the time coordinates first on both sides of the equation. And now we see from Alice's metric equation that minus dt squared plus dx squared is equal to negative d tau squared, so we can make that substitution into this equation. This is Bob's metric equation using his Rindler coordinates, and it tells him what anybody's proper time is. It can also be used by anybody else who's accelerating with constant rest frame acceleration a0. The primes in this equation are not necessary, so let's suppress them for convenience. Now that we have Bob's metric equation, we can use it along with the geodesic equation derived in a previous video to describe the motion of Alice or any other inertial observer. Let's see how these equations can be used together to describe the motion of Alice. Our geodesic equation is actually 4 equations because alpha can be any of Bob's 4 coordinates. Let's choose alpha to be equal to Bob's time coordinate first. Now remember, G is the metric tensor, which is a matrix of the dot products of the basis vectors, and we can find its components by looking at the metric equation. Recall our example from a previous video that ds is equal to dx ex plus dy ey, where ex and ey are the basis vectors covered in a previous video. So ds squared equals ds dot ds, or dx ex plus dy ey dot dx ex plus dy ey, which expands out into this expression. Now in Bob's case, his coordinates are not the Cartesian coordinates x and y, but the Rindler coordinates t and x. So let's make that change. Now let's say that Bob is observing Alice as she travels through space-time, and he is using his Rindler coordinate system to keep track of her motion. Then in that case, the invariant quantity ds squared that this equation is describing is given by the left-hand side of Bob's metric equation, namely the negative of Alice's squared proper time. So let's make that change in notation. Also remember that the metric g is given by the dot product of the basis vectors. So et dot et is gtt, ex dot ex is gxx, and et dot ex is gtx. Comparing the two equations, we can find the value of gtt, gxx, and gtx. Now we can put these values of the metric tensor into the geodesic equation. We are summing over the n's in the first term, so it expands out into d by d tau of gtt dt by d tau plus gtx dx by d tau. Now gtx equals 0, so the second term vanishes. And none of the metric components are explicitly dependent on t, so the last term vanishes. If the proper time derivative of the expression in brackets is 0, that means the expression is a constant. Let's substitute in the value for gtt. Now the constant that appears on the right-hand side of this equation depends upon the initial conditions of Bob and Alice. When Bob accelerates back towards Alice, he momentarily sees her come to rest at a maximum x-coordinate x0. So when Alice's x-coordinate is x0, her proper velocity dx by d tau equals 0. Then dividing Bob's metric equation by minus d tau squared helps us see where to apply these initial conditions. When Alice is at x-coordinate x0, she is at rest with respect to Bob, so dx by d tau is 0. Now let's take the square root of this equation and multiply both sides by negative 1 plus x0 a0. Comparing this equation with the one above, we can identify the constant c as negative 1 plus x0 a0. So let's make that substitution. Now let's rearrange and solve for d tau. Now we square both sides. And now we make this substitution into Bob's metric equation. And now let's rearrange the formula to get ready for integration. Factor out the 1 plus x a0 squared dt squared. Divide by the expression in square brackets, and take the square root of both sides. Let u equal what's in the square root. Then du is this expression. Let's solve for dx, and then substitute this back into the original equation. Let's bring the negative a0 over to the other side. Now let's solve for 1 plus x a0 squared in our equation for u. And now we substitute this back into our equation to be integrated. To solve this integral, we make another substitution and let u equal 1 plus x naught a naught hyperbolic tan w. Let's square both sides and make the substitution. Let's factor out a 1 plus x naught a naught squared from the denominator. Now we need to change du into dw so that we'll be able to integrate. So let's take the derivative of this equation. Now let's make this substitution. Here, let's use the identity that 1 minus hyperbolic tan squared w is equal to hyperbolic secant squared w. Here we see that numerator and denominator cancel, and we're just left with negative a naught dt is equal to dw. Integrating both sides yields minus a naught t is equal to w. Now let's take the hyperbolic tan of both sides. And now let's use the fact that hyperbolic tan of a negative is negative the hyperbolic tan in order to move the negative sign out in front. Now let's multiply both sides by 1 plus x naught a naught. And we see that the right-hand side of the equation is just u, which in turn is just the square root of 1 plus x naught a naught squared minus 1 plus x a naught squared. Let's square both sides of this equation. And now let's bring the terms involving x to the left-hand side and the terms involving t to the right-hand side. Now we factor out a 1 plus x naught a naught squared on the right-hand side. And now we use the identity that 1 minus hyperbolic tan squared is hyperbolic secant squared. Now let's take the square root of both sides of the equation and divide everything by a naught. And finally, let's move the 1 over a naught from the left-hand side to the right-hand side. This is our final result for Alice's position as a function of time according to Bob. As you may recall from the video The Twins in Rindler Coordinates, this is the same result for the motion of Alice that we found in that video. The negative sign differences are simply due to the fact that we kept a naught and x naught positive in that video, whereas in this video x naught and a naught are negative. We showed that given Bob's metric equation in Rindler coordinates, we can use the geodesic equation to derive Alice's motion in those coordinates. This is the machinery of general relativity. As you can see, it is not particularly useful in the case of Alice and Bob, because it was easier to just use the Rindler coordinates themselves to derive Alice's motion, as we did in a previous video called The Twin Paradox in Rindler Coordinates. However, the machinery of general relativity becomes useful when spacetime is curved and the flat spacetime equations no longer apply. In that case, we must use the machinery of general relativity to solve for the motion of inertial objects, which we will do in our next video. Thank you for watching.